All right. So we were discussing about the encoding instructions, and we were looking at the basically SimpleRISC instruction set architecture. So we looked at that there are 21 instructions that can be for that we need five bits to represent those 21 instructions. So that means our opcode needs to be of 5 bits. Now we are left with 27 bits because our instruction is of 32 bit long. All right. So we since we wanted to discuss about the modifiers, that's why we directly jumped onto the instructions where there are 3 operands. So that's why we looked at instructions like this, where the 3 operands can be registered, and we have gone through them in detail. Similarly, if the 3rd operand is basically immediate, then also we have seen how we can use these values. All right. Now we have skipped few things. So there can be instructions where basically there is only maybe one operand that need to be specified. For example, you can have instructions like call, branch if equal, branch greater than. So in these cases, so you have this 5-bit opcode, and then you are left with 27 bits, and those 27 bits can be used for denoting the basically the address where you want to go, right? So basically they generally, these 27 bits will be used for generating the offset. So let me write it in a different page. Okay, so we are talking about instructions where like call, branch if equal, branch greater than, this kind of instructions where basically the fields which we need are like this. So you have opcode, and then you have this 27 bits for offset. So offset with what? Offset with the basically PC, because whenever you have a call instruction, you need to go to a different location. Now in this part of the instruction, you will have the offset stored, which will be basically adjusted with the PC program counter, so that you know that where from you have to get the next instruction. Similarly, in case of branch, this 27 bits can be used for denoting where you need to go, and again it will be an offset, and basically the addressing you will be using is basically the PC relative addressing. So this is your 27-bit offset, which will be added, subtracted with the PC to get to the new location from where you have to get the information from, or get the next instruction from. So this is a basically signed number. All right. So that's why you can go basically add something with PC, or you can subtract something from PC. Now generally the instructions are basically, all the instruction addresses are addresses are a multiple of 4, because each instruction is 4 byte, right? So if I just list down all the instructions, their addresses will be multiple of 4, because each instruction will require 4 byte to store. So if this address is, let's say 1000, so this will be 1004, 1008, and so on, right? Because this is 1001, 1002, 1003. So one thing to observe here is that that all these addresses will be basically multiple of 4. That means what? That means the lowest significant or least significant 2 bits will be always 0, because if a number is always multiple of 4, that means the least significant 2 bits will be always 0, because what is 4? 100, right, in binary. So that's why you can say that this offset actually in the within these 27 bits, the offset you represent the actual address you can get by multiplying it by 4, or basically shifting it by 2 digits. So what it means is basically you can address all these different location using this 27-bit offset, which you can add or subtract with PC to find out where you have to get the next instruction from for this call, branch, instructions, etc. Okay. So the actual address which will be computed, the actual address will be PC plus offset multiplied by 4, because offset is pointing to an address which is where the least significant bits we are ignoring because least significant bits are known that they will be 0 only. So the actual address you can find out by this. I hope this makes sense.
Sir, what is PC means PC address?
PC is the program counter, right? Like the program counter, which is indicating which is the instruction I am currently executing. So I have list of instructions.
Opcode, sir. Program counter means opcode, which we have done yesterday.
Yeah, basically where from you will get the instruction. So the instruction has opcode, the operands, this whole 32-bit. Now where this is stored somewhere in memory. Now how do you know where is it in the memory? So this PC is a register which holds the address of this instruction, so that you can figure out, like, okay, I got this instruction, now what is the next instruction I should execute? So that I'll get to know by adding +4 with PC. So if there is no branch or anything, so the next instruction is basically at an address which is PC +4, because each instruction takes 4 bytes. All right.
Yes, sir.
Yeah, Chirag.
Like, can you like explain it again? Like I'm not still clear. Like what were you like making us understand by the like right part, like the 1004?
Oh, okay. So what I'm saying is that, see, these instructions, call, etc., will indicate where you need to get the next instruction from, because call is call, branch, these instructions, you read the opcode, you realize that, okay, I have to now update my PC to get the next instruction from a different location other than PC +4. Now where is this? That is denoted by this 27 bits. This is a signed number. So now with this 27 bits, how do I calculate the new address of my PC? So that is done by adding to my current PC this offset value. Now offset value is 27 bit. Now we are saying that all these addresses where my instructions are stored, they are always multiple of 4, right? Because each instruction takes 4 bytes. I'll not have an instruction address which is pointing to this location, right? So now why this is important? So that means that these addresses, always the lower significant 2 bits will be 0, because they are always divisible by 4. So if I write a binary number which is divisible by 4, that means the least significant 2 bits are always 0. All right. So since these least significant 2 bits are always 0, that means I can I can address to a much larger, at least 4 times larger space than what I usually could have done with 27 bits. If this was not the case, with 27 bits, how many different addresses I can point to uniquely? I can point to 2 to the power 27 different locations, right? Now what? So I'm ignoring the sign bit. You can be more precise, and you can add the sign bit, and you can make it 2 to the power 26 and so on. Now we are saying that, okay, we always know the address, last 2 digits of the address will be always 0. So what I can do, so this is what I can do with 26 bits or 27 bits. Now I know the last 2 digits are always 0. So I can basically just ignore those last 2 digits, and whatever offset I have, I multiply it with 4 and then add it with PC. That gives me the actual offset, actual address from where I should get.
So, sir, you are not storing the 2 LSB zeros, right?
Yeah, because why should I store it? This is always known that it will be 0.
So you can accommodate more number of addresses by doing that.
Yeah.
So is it necessary like that, like this multiple of 4 thing, like that would be applicable only if the addressing starts from 00 only? Like your starting address was 1000, right? But what if there was a previous address stored there and that is not a multiple of 4 then?
Then it will not be the case, but generally you will not have. So okay, maybe your address will start from 00. Let's say instead of 1000, it will start from 00, right? You will not, basically it will be very unlikely that you will start an address which is, let's say, somewhere here. Then of course you have to basically that will be a very complicated, or not complicated, that will be an unnecessary implementation, which where you will not be able to exploit. You will be able to exploit, but then to exploit that you need to do a lot more than just ignoring the least significant bits. You can always add that additional offset which you need to add in those cases, but that is unnecessary, right?
Yes, sir, got it. Thank you.
Yeah, Ashwin.
So, could you please explain that 2 LSB zeros which you were telling, sir? I didn't get that.
Because this, see, each instruction requires 4 bytes. And our objective is to identify each instruction, or our objective is to denote addresses for each instruction. So if I have an instruction at this location, the next instruction will be only after 4 bytes. So that's why the next instruction.
Okay.
Yeah.
Yes, sir.
Sir?
Yeah.
Sir, you said that the program counter points to the instruction, means to store the address of the instruction, right? So, sir, which component will scan the whole instructions, means?
Which component?
Scan the whole instruction, means what is the instruction is like? Which component scan the whole instructions, means interpret the instruction assembler?
I'm not sure I got your question, but if you are asking that, okay, I have this instruction, let's say, so it's kind of, let's say, on your power, when you power on your processor, it has a basically by default address from where it starts getting the instruction to execute. Are you hinting towards that, or you are saying like are you indicating that where from I'll know this offset and all these things? I'm not.
I'm saying that when the program counter comes to a particular instruction, then it will have to, we have to see that what is the opcode for, like, depending on the opcode the instruction is particular. So who check that opcode, that instruction, the offset?
Yeah. So there, first thing you will, so there is a fetch unit. So we'll talk about it when we talk about the hardware implementation. So remember the analogy we talked about. So there is the mesh analogy we talked about. So there you will have this instruction execution divided into multiple subparts. So first you will bring, depending on the PC, you will bring the instruction which you need to basically you need to first fetch the instruction. After fetching, you will decode. In the decode stage, you will look at what is the opcode, what are the offset, what are the different operands, and so on. All right. And once that is done, then you know that, okay, where the offset should be and all these things.
So, sir, the program counter doesn't decode anything, even the opcode, right?
Program counter is a register.
It only shows the address of the instruction which is to be executed.
Yes. All right. So I'll move ahead and so there is so we have looked into the two instruction cases where there is basically the three operands where one of the operand can be immediate as well. The things which we could not look at in the last lecture was instructions like this, which has only two operands. Now in this case, we are looking at instructions like compare, then not and move kind of instructions. So here you see that depending on what instruction you are looking at, so there is opcode. Then if there is an immediate value which need to be compared with, then it will be indicated by this I. And then there is your the values you need to basically there is no destination in compare instruction, because you are not putting anything in storing anything, you are just updating some flags. So this is source 1, which is a register, and source 2 can be an immediate or a register. Similarly, move instruction, you have a destination and you do not have basically you do not have two sources here, you have only one source. So one source can be the register or the immediate. Similarly, in not operation also you have only one source and one destination. All right. So I hope this makes sense. We have also looked into the load and store instructions. I'll just very briefly talk about
then
it.
what we will do in place of the register then, if we don't have that register?
You tell me what you will do. Let's say your decoder decodes that this is a compare instruction. What you will do?
We can simply skip.
Mm-hmm.
We can simply skip.
So this is very intuitive, right?
Yes.
As soon as you decode that this is a 2 operand instruction, you know which are the locations or which are the fields which you need to look at, and look at them and do the things. All right. Okay. So the load instruction, we have seen it in the last class also. So you have a destination, you have your basically if you are your load instruction, the address which you are specifying where from the load needs to be done through this offset, basically base offset addressing mode. Then there is a immediate value which is indicating the offset, and the source register 1 is storing the base value, and using them you can find out where to get the immediate value from. Yes, Ashwin, very quickly, because I have to cover a few things, and even if I don't get time, I'll put the videos, so that will be in syllabus.
Oh, okay, sir. So I'll ask it fast then. Sir, could you like the move instruction and the store instruction, sir? They seem to be very similar. Like you're moving values into the registers, right? Like in a move instruction and store. So like, what is the difference, sir?
No, so load, generally you do use it for loading data from memory. So whenever you need to populate your registers or populate your registers, you have to use this load instruction. Move is moving values generally from registers within registers, or quickly moving some, let's say, immediate value to some registers and all these things. So that's move. Load is primarily for memory related, memory, basically reading memory and storing the value from memory.
So can you say move is only used for constant values, but load will be used for register, like that, can we say? Like immediate values only move can take, can we say?
I would rather say that load is used directly for accessing data from memory, which is not true in case of move.
Okay. Thank you, sir.
So stored instruction we have also discussed in the last class. There we have to make some exceptions, because here in load instruction you have two registers. So basically there is RD, basically there are two registers, but both these registers are nothing but source registers, because this is the destination. This address is the destination where you want to store the data, and the source of the data is this register RD. So to do that, basically you have to break the protocol a bit, and in this destination register, actually you are storing the value, or you are indicating this register. So this register, though in this format, is denoted as destination, but it is not destination, it is actually the source of the data which need to be stored. So this is one exception in case of stored instruction. I hope you guys can you guys understand that what is the difference. So though we are denoting it as RD, actually it is not a destination register. It is the source of the content which need to be stored in this address. But since we have this format where I can only deal with two registers and one immediate value, now here the two registers are basically my source registers only, but I can only accommodate in this format one source and one destination. So what do we do? We say that, okay, in this field where we are supposed to store the destination register, here also we stored this value, which is basically a source register. So that is the compromise we make, just to make sure that our hardware does not become too complicated, just for this store instruction. All right. Okay, so don't have to overthink this thing. So here our objective is that, okay, store has this format. This is the destination. I can't put the destination field here. So destination is denoted by the immediate and the source register. So I'll put them here only, and I'll do the function appropriately. But while I decode this, I know that, okay, this RD is actually pointing to the register where from I have to read the value and store it. All right. Okay, so just to quickly summarize, this is how our instruction format looks like. So for branch, for all instruction, there are 5 numbers which are 5 bits which are reserved for opcode. So all these 5 bits are 32 to 28, these 5 bits. And for branch, compare, branch, jump, call, this kind of instruction, the rest of the 27 bits are used for offset. In case of basically instructions where all 3 registers are used, there you see that this first 5 bits 32 to 28 are used for opcode. Then there is a single bit which indicate whether there is an immediate operand or not, then there are destination register and the two source registers. Immediate, so again this still remains same, only difference is that you have a immediate address with the modifier stored in this 18 bits. All right, so I think we have spent enough time on these things, so I'll pause for any quick question and then we'll move to functions.
Sir, what is this 28, 32 written in the brackets?
So you remember that we have 32 bits, right? So let's say this is bit number 1 and this is bit number 32. So 32 to 28, these 5 bits are reserved for my opcode. All right, then there is this 27th bit, which is basically either I or if there is an immediate operand, then it will be denoted by I. I will be 1. If not, then I will be 0. Followed by that, I have 4 bits for destination register. Followed by that, 4 bits for source register 1 and 4 bits for source register 2. Then you are done with this. If you have an immediate, then you will need to use the rest of the bits.
Yes.
All right. Yeah.
Excuse me, sir.
Yeah.
Sir, in the store instruction, why are we storing the immediate value?
Because the addressing in store can be of this format, right? Where basically we have this base offset addressing mode. So the immediate indicates the offset. You remember, like we have in several discussions, we told about that generally if you are accessing an array, so you want to access the multiple entries of that array. Now the base address will be storing the starting point of the array. Now if the array is containing, let's say, integer, then I know that the next element of the array will be base plus 4, and then the third element of the array will be base plus 8, base plus 12, and so on. So this 8, 12, these are your immediate values. So these are generally represented using immediate values. In this way, the addressing becomes much more systematic and simpler.
So for storing something, first we need to know this from where we want to store the value and the destination. So if we have both of them, then what is the need of immediate?
No. So let's say I want to store my results in an array. All right. So then the first outcome I'll store in the first element of the array. Second outcome I'll store in the second element of the array. Now, if I want to store these results in an array, then this addressing mode becomes much more simpler or easy to implement compared to any other addressing mode. Otherwise, you have to basically spend a lot of time in figuring out where is the next location where you have to store the value. Right?
Okay, sir, got it.
Okay. All right. So